So here we go with the second example, or example 9 as it is in the textbook. A particle P is moving. So let's pick out the key information again. Particle P is moving in a plane at time t seconds. Its acceleration is given by 4I minus 2j. When t equals 3 seconds, the velocity is 6I, so velocity is 6I. And the position vector we're given as well with respect to a fixed origin O. Find the angle between the direction of motion of P and I when t equals 2. So the direction of motion tells us that we need the velocity. So we need, don't know what's going on there. So we need V for that at t equals 2. And the other thing to pick out from here is here, A is a function of t, therefore not constant acceleration. So we're going to have to remember our key facts that keep coming up at the moment are V, A. In that direction we differentiate with respect to t, so in this direction we're going to integrate with respect to t. So here we go again. A is equal to 4I minus 2tj. The integral of A with respect to time is equal to the velocity. So we get 4t plus a constant, lots of I, plus, write down the constant, minus 2, add 1 to the power, divide by the new power, plus another constant, C2, lots of J. So we need a constant again. Yeah, we need a constant again with both the I and the J term. So, what are we going to get here then? Presumably we're given some boundary conditions, because if we need it when t equals 2, we've got to find the values of those constants. So if we read back, we're told at t equals 3, v is equal to 6i. So at t equal to 3, v is equal to 6i. And although it doesn't say it, it implies very strongly that 0j. So if we now look at our I component, so for our I component, we get 4t plus c1 is equal to 6. T is equal to 3, so we've got 4 lots of 3 plus C1 equals 6, so C1 equals negative 6. Let's look at coefficients of J, or the components of J. It's just a different way of saying the same thing. We're going to get 0 is equal to, minus 2 over 2 is minus t squared, plus C2. So let's just go back and show you clearly where those came from. So the J component, 0, and gives us that. I'm just going back one step further. The I component is going to give us that. I hope that's clear. Okay, now back down to considering the coefficients of J, or the J component. This was at t equals 3. So naught equals minus 3 squared plus c2. Now there's a deliberate error in there. Where's the mistake? I hope you spotted it. The 3 should have brackets. Whoops, the 3 should have brackets around it. So we get minus 9 plus c2. So c2 equals to 9. So now we can write out our new vector v. We've got 40 minus 6 for the I component, plus, I can write this as minus t squared plus 9, lots of j. You might have chosen to write that as 9 minus t squared. That would be absolutely fine. Okay, so we've found the velocity. Let's go back and read the question, make sure we've answered it. Find the angle between the direction of motion of p and I when t equals 2. So we need the velocity at t when t equals 2, and then we need to find the angle. So at t equal 2, v is equal to 4 lots of 2 minus 6i plus minus, remember the bracket in for the t again, plus 9j. So we end up with 2i plus 2 squared is 4, negative 4 plus 9 is 5j meters per second. But we didn't just want the velocity, we wanted the angle with I. So let's draw out our diagram. That's 2 in the I direction, if that's I and that's j, which is our usual definitions. And then it's 2i plus 5j. Notice how we add them up. It's the 2i. Yeah, so it's the 2i plus the 5j to create the vector v. And we want the angle with the I direction, so we can call that theta. Tan theta is equal to, well, I'm sure you're confident with this stuff now, opposite over adjacent. So we get tan theta equals 5 over 2. But we want the angle, so theta equals arc tan of 5 over 2, which you can tap in the calculator. It's going to be around 65, 70 degrees. Let's just check, 68.2 degrees. Okay, there we go for that. Now, because it's defined in the question, I've got the diagram, I'd probably get away with that as an answer, but I much prefer you as habit, because we want a direction. I would then want to say anti-clockwise from positive I. I mean, that's defined really in the question, but as a habit, 68.2 degrees is an angle, it's not a direction. So you've got to give it relative to something to make it into a direction. Okay, let's go back. We've got a second part to this, B, the distance of P from O when t equals 0. So the distance of P from O when t equals 0. So we've got to now get to the distance. Well, we know the distance requires us to know the position, so we've got to integrate the velocity to get to the position. We've already highlighted that at the top of the page. So that's going to equal r, and 4t minus 6. So write down the constant, add 1 to the power, divide by the new power. Minus 6, the integral of negative 6 is negative 6t. And then we need a constant of integration plus I shouldn't use C because I've already defined C1 as a value last time. So last time it came out as -6, so I need to use a different letter. So I'm going to call it D1, lots of I. Now look at the J component. We've got -t squared, so it's plus -1, add 1 to the power, divide by the new power. Plus 9 gives 9t plus d2. Same argument about the constants. Okay, so we've got a vector for r. Let's just tidy that up. 4 over 2 is 2, so we've got 2t squared minus 6t plus d1, lots of I, and plus -t cubed over 3 plus 9t plus d2, lots of j. That didn't tidy up very much, but it just out of habit that we should be doing that kind of thing. Okay, so now the challenge is to find d1 and d2. Let's go back to the question and see what we're told. We are told that the position vector of P at t equals 3 is 20i plus 3j. So at t equals 3, r was equal to 20i plus 3j. I hope I've remembered that correctly. Let's just check. 20 plus 3, yes. Okay, so usual approach, we can now look at the coefficients of I, or the components of I, at t equals 3. So the I component, again, if we come back in here, we can pick these out. The I component and the I component is going to give us this statement. So we've got 20 is equal to 2, t is 3, squared minus 6 lots of 3 plus d1. So we get 9, 18 minus 18 plus d1. So d1 equals 20. Coefficients of j, using the same idea. So for j, we've got that statement, we've got 3. So that's going to give us 3 is equal to negative t, which is 3 cubed over 3, plus 9 lots of 3, plus d2. Okay, so next now we need to just tidy that up. So 3 is equal to negative 27 over 3 is 9, or one of the 3's cancel, plus 27 plus d2. So d2 is equal to 12, take away 27 is minus 15. So we've now got r is equal to r is equal to, what have we got there? 2t squared minus 6t from just at the top of the screen, plus d1, which is plus 20, lots of I, plus negative t cubed over 3 plus 9t minus 15, lots of j. Okay, let's go back, check the question, see if we've answered it. The distance of P from 0 when t equals 0. Okay, so we've got to put it in, substitute t equals 0, and it's distance, not the position. Notice, need distance not position. So distance is equal to the magnitude of r. Okay, so at t equals 0, r is equal to 2t squared, oops, got to substitute in the 0, let's put it in a bracket, 0 squared minus 6 lots of 0 plus 20 I plus negative 0 cubed over 3 plus 9 lots of 0 minus 15 lots of j. So work that out, that's 20i minus 15 j. But we want the magnitude of r, because the distance then is equal to the magnitude of r. So that means using Pythagoras, so it's 20 squared plus negative 15 squared to be precise. But when we work it out, hopefully you spot the Pythagorean triple. 3, 4, 5, so that's 5, that's going to be 25 metres. Okay, hope that's helped.